Okay, so if we put these into the calculator, did you get an answer on this one? Everybody get an answer? So we would just go to the matrix screen. We'd edit matrix 1 to be, what would the dimensions be of the echelon form matrix? 3 by 4, good. So 3, enter, 4, enter. Oops, screwed that up. 3. And then what? 1, -2, 3, 9, -1, 3, -1, -6, 2, -5, 5, 17. Okay? And what do we do next? Got to quit. Good. Matrix. Math. Good. RREF. Reduced row echelon form of matrix A. Oh, I did C. Whoops. I don't know why I did C. Matrix C. Okay. Normally that'd be A. And then we hit enter. And so what's that tell me? Yeah, good. So this is telling me then that, look at that first row. This is the A column, B column, C column, right? Coefficient of X, coefficient of Y, coefficient of Z, and then whatever's on the other side, the equal sign, the constant. So this tells me 1 times X equals 1, 1 times Y equals -1, 1 times Z equals 2, right? I think there's a way. What do I do?
Is there a certain mode you have to be in for this to work?
Yeah, there is. There's always. I always forget them too.
Because I'm getting -59, -13, 14.
What?
And I did the same thing happened.
Yesterday?
Yeah.
Come show me. Let me take a quick look. No, there shouldn't be a mode for this, I don't think. Okay, so let me see your matrix B. Matrix B.
No, you gotta go to edit.
I can do that. One, is that right? 1, -2, 3, 9, -1, 3, -1. This would be -6.
Oh,
That's
there
why.
we go.
Yeah, that's it. Okay, so capture this. So then that's telling us that the solution, written as an ordered triple, right? The solution is just 1, -1, 2. Okay? Try this one. What would happen if I were like missing a z in that first equation?
Just put a 0 for
But I
it.
put a 0 for the coefficient of z then, right? Okay. Oops, I'm done. What am I doing? Okay, so I got that matrix in there. I got to quit. And then I think I can just go up and grab that. Yeah, that works. Okay. Oh, well, good enough. Okay. Okay, what in the world does this mean? Everybody interpret that for me? What's that mean? What's his first equation telling me?
1 times x plus 13 times z equals 0.
Second equation.
1 times y plus 4z equals 0.
Third equation.
0 equals 1.
Okay, what the heck? What's that mean? What's that always meant in the past when we get a true statement? Not undefined.
No,
It means, like if we had done, well, what if we did a linear equation, like let's say we wanted to do, we're solving the equation, let's say 2x plus 3 equals 2x plus 5. So we're finding where the line y equals 2x plus 3 crosses the line y equals 2x plus 5. What do we get?
doesn't cross.
Yeah. So what do we say?
Parallel lines.
Parallel lines, but what do we say in terms of a solution set? There is
No solution.
no solution. Right, so there's no solution here. To be more precise, what we would say, in math, we would label this an inconsistent system. So remember we talked about yesterday, a linear equation in 3 variables. Linear equation in 2 variables is a line embedded in a plane, right? What's a linear equation in 3 variables? What did we say that was?
Plane.
A plane in a space, right? So the intersection of those 3 planes, each linear equation represents a plane. What's going on here with this? Is there a place, like if there was a single solution, like in our first example, that would be something like if we took the plane of the ceiling and the plane of this wall and the plane of the front wall, point to the place where the solution set exists.
That corner.
Yeah, that point in the corner where they all 3 intersect.
So would
Right.
this one be like the ceiling, the floor, and the wall?
Yeah, so it'd be something like that, like it could be the ceiling and the floor and the wall. So there are individual intersections between 2 of the planes, but all 3 of them never intersect at the same place. Or it could be like if you had a triangular tube you're looking down or something, right? So there's something like that going on. It's an inconsistent system because all three of them never overlap the same place. And where did you see that? You saw that from that third equation. It's always going to be that way. If you don't end up getting, you know that if you get the first 3x3 or the first square matrix, what if you're solving a 4x5 system? Or you're solving a 4x4 system. But if the matrix is 4x5 instead of 3x4, or 5x6 instead of 3x4, if you look at the first square part of the matrix, and it's an identity matrix, right? You guys talked about identity matrices last year? Okay. So then, if you get a diagonal of ones and all the rest are zeros, right away you know it's a single solution, and this is the solution right there, right? Easy. If you get a situation like this, where the bottom row, you don't have an identity matrix, but the bottom row is an untrue equation, like this, like you end up with 0 equals 1, then you know right away it's an inconsistent system, and there are no solutions. Okay, I got one more for you, though. Try this guy. You'll see this, if you study math, you'll see this again in college, I promise you. Try this one. Oh, I shouldn't have done that. Okay, so everybody got that, right? I'll show you a little trick here also. Though that's kind of inconvenient because those are written as decimals. Well, I think I can act on an object like a matrix, just like I can a number, and I can go math, convert to fraction, and look what it does. Okay, it gives it to me as fractions. Okay. So let's discuss this one. What do you think's going on here? Any ideas?
Is it infinite?
It is. It's an infinite kind. Yeah, you're right. And we can even go a step further than that. It's a great thing about linear algebra is that not only matrices are just awesome. Not only does it tell us it's infinite, but it's going to tell us how it's infinite. It's going to tell us what the dependencies are. Well, there's going to be. Let me take a picture of this. Talk about it. Paige, how did you get infinite? Because you're right.
The zeros on the bottom.
Ah, good. Zeros on the bottom, just like before, right? Okay, if you look at that bottom equation, what's that bottom equation saying? Yeah, it says 0 equals 0, and just like before, what did that tell us if we solved a linear system and we ended up getting 0 equals 0? Well, that meant same line, didn't it? Right? Infinite number of solutions. Same kind of thing here. Only in this case, it's not necessarily the same plane. But give me an example of how there could be an infinite number of solutions when three planes intersect. They could be the same plane. In this case, they're not. if they intersect, well, yeah, if they intersect like if I did something like, here's two planes intersecting, right? If you look at it like that. Now, what if I just added a third one that's tilted at a slightly different angle, right? See what I'm saying? So they all intersect along a single line. Now, look at look at what this tells us. This is really interesting. You're going to have a lot more insight into this when you get to college and you study this for more than just 20 minutes. Yep.
So, can you assume that two of them are the same plane?
No, not necessarily. I mean, it could be that two are the same plane, but in this case, none of them are the same plane, I don't think, in this case. What do these equations right here say? X minus 2/3 z equals 0. And what about this one?
Y minus 5/3 z equals 0.
Okay, what are those? This is telling us that
Are those
They're
the
slippery.
lines where it's, where it has infinite solutions?
yes. Yeah, these are the places where, so this is telling us that z, we can pick any value we want for z. If we pick any value we want for z, we can use these two equations to find the corresponding values of x and y. Okay, but look how the values of z are linked to the values of x and y by two-dimensional linear equations, right? And so what this means is there's some line that's traveling through all three of the planes, right? It's traveling, if I look at an XYZ axis, something like that, right? The lines aren't embedded in any one of those planes, right? They're traveling through free space and they're going to intersect all the planes. See what I'm saying? They have a trajectory in all the planes. And so that's what this is telling us. But you'll see that, once again, you'll see that again in the future. How would this be important though? Because a lot of times we don't really care about the geometry of this situation. We're solving a real world problem. Maybe it's an economic problem or something, right? And if you've got these constraints that give you these three equations, and I get some kind of a relationship like this, well, this is important because this tells us right here, if I solve for x, that's telling us that x equals 2/3 z, right? X and z mean something, right? Those x's and z's in our problem, maybe it's the price of a certain kind of widget and the price of another. I mean, this is telling us it's linking. Mathematically, it's linking in this solution that we found, it's linking those two variables in a way that they're dependent on each other. X is also dependent on, or Y is also dependent on Z, right? See how that works? So this is telling us right here, this one tells us that Y equals 5/3 Z. So yeah, there's an infinite number of solutions, but those solutions have specific constraints. These are the constraints. X always has to equal 2/3 Z, and Y always has to equal 5/3 Z. Right? See how that works? So, I mean, just wanted you to see that. There's more to that reduced row echelon form than just finding solutions that work. Okay, so moving on. Anything else from the assignments that we need to hit? How about the 3-4 assignment? Anything on the 3-4 assignment? How are we doing on that one? Do we need to take a look at that one just real quick? Should I pull it up and we'll just look through it and see if there's... I'll do that. Because I want to move on and cover something else, but I want to just make sure that if you have some questions about this other stuff, we're dealing with those too. Excuse me. Okay, when they ask for concavity, how do we find concavity? Let's close up these Chromebooks real quick. How do we find concavity? Third row. Yeah, it's the Y double prime row, right? Or F double prime, whatever you want to call it. The bottom row in our table. Where it's positive, it's what? Concave. What's positive concavity? Concave up.
And then negative concave down.
Negative's concave down. What's our test for concavity? How do we know at a given point? Like if I
If the
have a
value,
function here.
if the value of the second derivative of the function is positive, it's concave up.
True. What does that mean in terms of a graph? Like if I'm looking at, just a little review. So say I've got some
Tangent line is
function.
above or below
Say it again.
this. The tangent line is, it will be either above or below.
Above or below. Yeah, so for example, at this point right there, the tangent line sits below the curve, and so the concavity is up, positive. Right up here, it's negative, and where does it flip? Well, right about there-ish, right? So here's positive second derivative, there's negative second derivative, right? And that would show up on our table. What would have to be happening right there? What do we call that point?
Inflection point.
Inflection point. Good. Okay. Points of inflection, where do points of inflection occur?
When the second derivative equals 0.
Or possibly, we looked at one weird example
When it's
where
undefined.
it's undefined, right? So remember, there's this parallel relationship, right? All the stuff, you guys know the first derivative stuff really well, right? But if you know the first derivative stuff, you can just shift that up by one order of derivative, and it has a parallel relationship with the second derivative stuff, right? First derivatives, quick review. First derivative has to do with what we use to find extrema, right? Relative extrema can only occur at what kinds of numbers? Critical numbers. All critical numbers may not pan out, right? But if we make a list of critical numbers for the first derivative, I can just test each of those critical numbers, and if I test all of the critical numbers on my domain, I'm guaranteed to find all of the relative extrema. Some of them may not pan out, some may be false alarms. Same thing is true for second derivatives, right? We'll find a list of second derivative critical numbers. And just like first derivative, critical numbers occur where the derivative either equals or is undefined, right? Same thing for second derivative. If we find all the places where the second derivative has zero value or is undefined, that's our list of second derivative critical numbers. All of the points of inflection would have to occur at one of those places, right? Does that make sense? So it's the same kind of an approach. Okay, let me just zip through this and see. Whoops. Okay. This is a good problem. We're supposed to estimate where the graph is first and second derivatives are positive and negative. Okay, so let's do first derivatives first. So let's just split this into segments where the first derivative is positive and negative. Where's going to be a transition? Okay, about, hang on, no, for first derivative.
Where it crosses the x.
No. Okay, at the first relative extremum, right there, right? So right there, we've got a transition. To the left of that, what's the sign of the first derivative? Positive. So over here, f prime is greater than 0, right? Where is it negative? From negative 3.1-ish up to about what?
About -1 or negative.
So close to -1, right? So there's our minimum. So right in between those lines, we've got f prime is less than 0, and then over here, f prime is greater than 0 again, right? Okay. What about the second derivative? Change colors. For the second derivative, where is the second derivative positive?
To the right of it.
Okay, so there's my point of inflection, so that's gonna be the boundary, right? Everything to the right of that, we get positive second derivative. To the left, it's concave down, we get negative. Okay?
Okay, what are the local maximums and minimums?
The,
Because-
where are they?
Yeah, I know where they are, but can you tell me where they are?
Yeah, they're the relative extrema, or the relative minimum and maximum. In this case, there's a relative maximum there, right? And a relative minimum there. Okay, because those are places where we're changing the sign of the first derivative.
On the online assignment, that's wrong. Is it the-
It is?
Yeah, it just gives it.
Which
So,
which problem?
3.3, question 4. It says that the answer is pretty much the x-intercepts.
Oh, okay. Well, hold that. We'll look at that. We'll go to that in just a second. Hold that thought. Let me just finish going through this one real quick here. Oops. Why did it do that? There we go. Okay, velocity and acceleration. What does that have to do with first and second derivative? If the position function is given to us, that's x, right? So it's position on the x-axis as a function of time. What's the velocity going to be?
F prime of X.
So it's going to be, yeah, it's going to be the derivative of that, right? The derivative of position is velocity, and acceleration
Second
is
derivative.
second derivative of position, which would be the first derivative of velocity, right? Okay, and so if we wanted to answer questions like, when is it moving in the positive direction? That would just be when the velocity is positive, right? So if we looked at the derivative, that would be where the derivative is positive, right? If we want to know where the acceleration is positive, that would be places where the second derivative is positive. So if I were to graph this function, those would just be, where it's concave up would be positive acceleration then, right? Concave down would be negative acceleration, okay? So physics types, I mean, think what that does to our algebra-based approach to physics. I mean, this makes it way, way better, right? When you can think of it in terms of calculus. Okay, I think we're pretty good on that. Okay, I think this is the table stuff, and I want to go through. Okay. All right, I think this stuff, we're going to do some more practice on this anyway. And then 52, there's the one we talked about the other day, right? Let's look at this other one Nick was talking about. 3.3, you said?
Yes. Question
3.3, question 4. This one, right? Is that the one?
Yes.
Okay. What are we supposed to find on this? Where the function is increasing, decreasing, estimate the x-coordinates of all local extreme values. Okay. So where is it increasing in this case?
Negative infinity to 0.
Okay, so negative infinity to 0 and
2 to
2 to infinity. Everybody agree? Okay. Decreasing from about 0 to 2. Okay, and then the coordinates of the extreme values would be 0, 3, and 2, negative 3. All right, so increasing,
your decrease.
that seems right, doesn't it? Increasing Oh. They got it backwards, didn't they? That does seem wrong. Where is it increasing? They said it's from -1 to 1. That is the
Here's
answer?
the graph of the function f prime.
Oh, yeah, it's f prime. Whoops, no wonder. Huh. It's f prime.
But that is f prime.
That's an easy one to miss.
But that
So-
one is f prime.
What's that?
But that function is f prime.
This is f prime, right?
So-
Okay, so this is a good one to talk about. So if this is f prime, this is graphing the values of this function are the derivatives, right? So where is this function, where is it increasing? Well, it's increasing where the derivative is positive. This is the derivative function. So where is the derivative function positive?
What's the water screwed?
Negative
Between -1 and 1, right? Or when x is greater than 3, right? Okay, so I see what you're, I got tripped up by the same thing. The issue here is this. It's that what's graphed is y equals f prime of x, not y equals f of x. See what I'm saying?
What number is
This is number 4. Okay? So what would the original function maybe look like then, if we were going to graph it? If this is the derivative function, what would the original function look like? Where is it going to have, where are going to be the relative extrema? -1, good. 1, and then 3, because those are the places where we're transitioning signs of the derivative, right? So what's going on at 1? If I'm going to superimpose the original derivative, what would it look like if I'm going from a negative first derivative to a positive? Yeah, that's going to be valid, isn't it? Right? So we're going to have, now the thing about it is, this is what we're going to learn pretty soon, is that we don't know where this thing sits in the, I mean, it could be shifted clear up here or shifted clear down here. We don't know, right? We only know within a constant. But we know what the shape of the graph is going to look like. It's going to have a minimum there. It has to have a maximum there, doesn't it? Because we're going from increasing to decreasing, right? So we're going to have a minimum, a maximum, and then it looks like another minimum, right? So our function would have to do something like this. If we wanted to work backwards and graph. Is that exactly what it looks like? Probably not. But it's the shape, the basic shape, right? Okay? Okay, anything else that came up we need to address on the homeworks? Nothing? Okay. Then what I want to do, I want to just take a real quick look. And we don't have much time today. We only have like, what, 5 minutes? Is that what we have? 6 minutes, all right. So you just tell me something, now we'll get into this tomorrow. But you tell me what is, see if you remember this from last year. If I've got a rational function, we're taking limits of rational functions. Tomorrow we'll expand this. At plus or minus infinity, okay? What's a rational function, first of all? What's the definition of a rational function? So if we're going to call a rational function, we'll call it r of x. How do we build the rational function r of x? Rational means ratio, right? So we know it's going to be something, some kind of fraction. What has to go on the top and the bottom for this to be called a rational function? What if I call the top p of x and the bottom q of x? What kinds of functions are those, do you know? Remember? Gotta be polynomials. So a ratio of polynomials is what we call a rational function. Okay, that's important because polynomials are well behaved, right? Polynomials themselves are everywhere defined and they're smooth, right? They're everywhere defined and differentiable, but the ratio may not be, okay? We've talked about this a little bit already. Where would we end up getting, if we have a rational function like this, tell me where would I get an asymptote?
Where q of x equals 0.
Where q of x equals 0 and p
P of x does not equal 0.
does not equal 0. So we'd get, does that make sense? We're going to get a vertical asymptote at a unique 0 of the denominator. So a place where the bottom polynomial has a 0 but the top does not. Where do we get a hole? In a place where a simultaneous 0 of the top and the bottom, right? Remember how we saw when we took limits, that was where we got the 0 over 0 behavior, right? Where would we get a 0 of the rational function? Where are we going to get a 0 of this function of r of x? Where p of x is 0, but q of x is not, right? So it would be a unique 0 of the top, okay? So then the next step is with rational functions, and I know you guys have done this, probably for the last 2 years, but see if you remember. So if I want to take the limit of, let's say, 2x squared minus 3x over 3x cubed plus x minus 11 as x approaches infinity, what's my answer? Do you remember? You guys should really close up. You're going to be missing some stuff here if you're not paying attention to this. So what's it going to be? What do you think? Still remember that rule? Okay, so let's derive it real quick. So what if I were to factor out, let's say, an x cubed? We can do it that way. If I factor an x cubed out of the top and bottom, what's left? Let's start on the bottom.
Can only do an x squared.
Oh, we can. If I factor out an x cubed, it just means I'm dividing each term by x cubed to find out what's left over, right? I could factor out an x squared too. It worked that way too, but I want to do it this way. If I factor out an x cubed, what do I get on the bottom? 3x cubed divided by x cubed is? X divided by x cubed is? 1 over x squared, good. And then 11 divided by x cubed is just 11 over x cubed. 2x squared divided by x cubed is?
2 over x.
Okay. Minus 3x divided by x cubed. Okay, so algebraically, we're taking a limit, right? So I can eliminate the simultaneous zeros. I can cancel the indeterminacy by just doing that, right? Everybody agree? We've done a lot of that stuff in the past. It's been a little while, right? But we cancel the offending factors. Okay, this is what we're left with. Now, in the limit that x goes to infinity, what is 2 over x? As x goes to infinity.
Really small number.
Yeah, so what's that approach?
0.
0, doesn't it, right? As the bottom of the fraction goes to infinity, the fraction itself goes to 0, right? Think about that. 2 over 10 is not that small. 2 over 100, it's getting pretty small. 2 over a trillion, it's getting really small. But there's no limit to how big the bottom is, right? So the size of the fraction just approaches 0, doesn't it? Right? So that goes to 0. So does that one, right? So does that one. And so does that one. So what are we left with in our limit? 0 over 3, which is, so tell me a rule here. If I take the limit of a rational function where the bottom is a higher order polynomial than the top, the answer is always going to be 0. Okay, we'll go further with that tomorrow.
Even if the top is larger than the bottom, would it be undefined?
Okay, if the top is